Greetings. I hope that you're staying warm. Because we don't have class tomorrow, I've decided to record the lecture. I will apologize in advance. I don't have a good microphone, and therefore you're going to be picking up some background noise, especially whenever I'm writing on my Surface Pro. At any rate, let's start with announcements like we normally do. Homework 3 is due on Friday. Get started on it. It may be a little bit more challenging than homeworks 1 and 2. Just keep in mind that a third of the points for the questions numbers on the homework require an explanation of the purpose of the question. Exam 1 is coming up. We'll be announcing review session times and locations shortly. Until then, please look at the study guide, practice exams, and the review worksheet that are currently posted. We'll post solutions whenever we get a little bit closer to the exam. Also, this Friday at 2 p.m. is the deadline for requesting an alternative time or for accommodations for the exam. So if you need to have accommodations, please make sure that you have the paperwork that's appropriate and stop by and visit with me. I also would appreciate having a grid view of your academic schedule from Access Plus so that I can find a time for you to take the exam. All right, keeping in mind for homework, please be nice to the TAs. Circle your final answer for calculation questions. Be organized and neat. Include units in your calculations. And please put your name on the homework. Otherwise, we won't be able to give you credit. And then the other reminder for all of the exams, if you pick up all of the graded homework prior to the exam, you'll get 1 point extra credit added to your score. The last time we met, we were talking about gas properties and gas behavior. We started with the ideal gas law, and we've pointed out that all gases behave ideally in the limit of low pressures. In order to help us visualize deviations from ideal behavior, we've introduced the concept of compressibility factor. The compressibility factor is given by Z, which is the pressure times the molar volume divided by the gas constant divided by the temperature in Kelvin. Whenever Z is equal to 1, we have ideal behavior. So what we've seen is that if I look at Z as a function of pressure, Z equals 1 corresponds to ideal behavior. What we've seen also is in the typical compressibility factor curve that we have negative and positive deviations from 1. We've seen that when the compressibility factor is less than 1, that's due to attractive intermolecular forces. Whenever the compressibility factor is greater than 1, that's due to repulsive intermolecular forces, which are associated with the non-zero or finite volume that the gas particles themselves occupy. We've introduced two parameter equations of state in order to describe non-ideal behavior. What we did last time was we've derived or pseudo-derived the van der Waal equation, and then we've introduced a number of other two-parameter equations of state. So we have the van der Waal equation of state, which we've pointed out is easy to work with mathematically. It's easy to justify it, but unfortunately it is not very accurate. For more accuracy, we need to introduce the Redlich-Kwong or the Peng-Robinson. We've pointed out, and we'll see today, that the Redlich-Kwong works best at high pressures. The Peng-Robinson is good near the liquid-gas equilibrium. We've also introduced the critical point. We've said that it's characterized by a single temperature, pressure, and molar volume, and that specific set of parameters are called the critical temperature, critical pressure, and critical molar volume. The other thing that's very important is that these equations of state that are cubic equations with respect to the molar volume describe both liquid and gas phases and supercritical fluid phases. And so all fluid behavior is explained by these equations of state, and that makes them pretty powerful. So the van der Waal equation, the Redlich-Kwong, and the Peng-Robinson all can be written in terms of polynomials that are third order with respect to the molar volume, and therefore they all three describe liquid, vapor, and supercritical fluid behavior. So some questions that we're going to talk about today, or try to answer today, is for these equations of state that are cubic with respect to molar volume, what information can we get out of them? Well, we know that if we have a third degree polynomial, there should be 3 roots. We're going to see that 2 of those roots are physically significant. Next thing, we're going to talk about the importance of the critical point. And we're going to see that that discussion is going to continue over a few lectures. We're going to introduce isotherms. Isotherms refer to constant temperature. And we're going to be looking at phase diagrams at constant temperature. From there, we're going to talk about how we determine the parameters. That would be A and B, or alpha and beta, for the 2 parameter equations of state. We're going to look specifically at the van der Waal equation. From there, we're going to introduce something called the law of corresponding states, which is pretty important. And along the way, we're going to introduce reduced pressure, reduced molar volume, and reduced temperature. All right, so when we look at the van der Waal equation of state, what we want are some equations that relate the critical temperature, pressure, and molar volume to our parameters A and B. And so the results of the derivation I've shown at the outset. All right, and so we can clearly see that if we know what B is or what A is, we can determine what the molar volume, the temperature, and the pressure of the critical point. Now, typically, we do this in a reverse way. What we normally do is measure the pressure, the temperature, and possibly the molar volume at the critical point, and we use that to determine parameters A and B. All right? Now, if you think about it, we have 3 equations here that relate A and B. And you should recall from algebra that if I have 2 unknowns, A and B, I only need 2 equations. So that means we have an extra equation. So we choose to use the one that is easiest to measure experimentally with high precision and accuracy. And it turns out that pressure and temperature are easier to measure accurately than molar volume. Right? Because if you think about it, we can use transducers to measure pressure and to measure temperature, whereas molar volume requires a special flask that has to be calibrated. And it's just more complicated. So we're going to be looking at pressure and temperature relationships. All right, so picking up where we left off last time, what I have shown in section 2.3 is a phase diagram. And basically, I want to describe a few points here. So I'm going to put an A labeling the intersection of the solid, liquid, and vapor phases. That's called the triple point. And the triple point has associated with it a specific temperature, a specific pressure, and a specific molar volume. All right, so that's described by 3 points, and it's fixed for a given substance. All right. The other point that we want to talk about, and this is what we're going to be focusing on primarily in this section, is point B. So point B is the critical point. And the critical point is, again, characterized by a specific temperature, which we symbolize with a subscripted C, and a critical pressure and a critical molar volume. Right? And so each substance, carbon dioxide or neon or argon, you name the substance, is going to have a unique temperature, pressure, and molar volume characteristic of the critical point. If I'm along the line segment A to B, if I'm sitting on that line, we expect our system to have both liquid and vapor present at equilibrium. Right? So what we're going to do is we're going to talk about, let's say we're going to start at this point. I'm going to label it with 1. All right? So for 1, there's going to be a temperature and a pressure that defines it. So there's my pressure, there's my temperature. All right? And it's pretty clear that that means that my system will be in the gas or the vapor phase. Now, if I choose to hold the temperature constant, meaning isothermal conditions, if I increase the pressure, that means I'm going to be moving in this direction. All right? So the only thing that I want to point out is as I'm moving to higher pressures at this fixed temperature, we expect the molar volume to be decreasing. Right? And then I'm going to reach this point where I hit the equilibrium line, and at that point I expect to see both phases present, the liquid phase and the vapor phase. And if you think about it, that means that I also should have 2 molar volumes, a molar volume associated with the liquid phase and a molar volume associated with the vapor phase. And we know that liquids are more dense than our gas phases, so our molar volume for the liquid phase will be less than that of the vapor phase. Now, if I continue along this trajectory, I will go into the liquid phase, and we no longer expect to see vapor present. All right? So what we want to do is look at how the pressure and molar volume are related. All right? And so what we're going to talk about is an isotherm. So an isotherm, as stated earlier, means constant temperature. And what we're going to be looking at is P, the pressure, as a function of the molar volume. All right, so that means I'm going to generate another phase diagram. So on my y-axis, I'm going to have pressure. The units will be bar. My x-axis will correspond to the molar volume, and that will be decimeters cubed per mole. All right? So if I again think about starting at this point 1, I'm going to call that T1. All right? If I start at low pressures, I expect my molar volume to be very large. So let me just remind us this. So as pressure goes down, the molar volume of our gas phase will go up. All right? So for T1, that means I'm going to start out here, all right, T1 there, right? And that will be my initial molar volume and my initial pressure. Now, as I move from point 1 and increase the pressure, I expect my molar volume to decrease. So we're going to show that, okay? All right, so this region is going to be described, we're in the gas phase, right? So we're in the gas phase, and this basically is just showing as I increase the pressure, the molar volume goes down. Now, when I reach the equilibrium point, liquid and vapor, I suddenly will see, in addition to the gas phase, I will see also my liquid phase, right? And as we stated a little bit earlier, we expect that molar volume to be less. So I'm going to come down here, and that's going to be my molar volume that corresponds to the gas phase, all right? And in equilibrium with that, I've got my molar volume that is associated with the liquid phase. Okay? Now, if I increase the pressure beyond that point, then I go into the liquid phase. And what we know about liquids is that they're not very compressible, so we don't expect the molar volume to change much. So there should be a sharp increase in our slope. All right? I'm going to put a dashed line in there just to indicate that that pressure And for that temperature, that's where I have equilibrium of both the liquid and vapor phases. Okay? So what I've drawn here is one isotherm. Okay? All right. So the other place that I want to talk about is if I was to do the same thing starting at the critical temperature. All right? So at the critical temperature, so I'm going to put TC on here. All right? I would expect I'm at a higher temperature, therefore, for the same molar volume, I'm going to have a higher pressure. So my curve starts up here, all right? And what we see is that as I increase the pressure, moving in this direction, I'm going to see a decrease in the molar volume, right? And then we're going to pass through this critical point. Right? And at the critical point, that's the last point at which we see any difference between the liquid and vapor phases. Right? And that means that we'll explain this again in a moment. That means that we expect to see just a basic point where I have both the liquid and the vapor. And then from there, I continue up with regards to my pressure, and the molar volume decreases. Right? If I go to temperatures that are greater than the critical temperature, then I have a supercritical fluid. And for a supercritical fluid, we don't expect to see no phase separations. So it's a single phase. And so what we really just see is that as we So this will be T greater than TC, so we'll call that T2, all right? So for T2, we basically are just going to see an increase in pressure accompanied by a decrease in our molar volume, right? So those are three isotherms that I've just drawn, right? Now I realize that that's not that meaningful by itself, so what I want to do is go to a better figure. So this is from the textbook. This is a series of isotherms for carbon dioxide. Okay, so let's talk a little bit about that. So the first point that I'm going to point out is the critical point. All right, and then what we have are two isotherms that are at lower temperatures. We have one at 23 degrees, one at 13 degrees. All right, so if I start at this end for both of these, I'm in the gas phase. That's what this G stands for, all right? And for both of these curves, as I increase the pressure, we see the gas behavior is going to cause a decrease in the molar volume, all right? And then when I hit the equilibrium line between the two, we start to see the liquid phase emerge. That's the other side. So this side of this corresponds to the liquid phase. All right. All right. And when I have a series of these isotherms, I can draw in this little dashed line. All right. And this dashed line basically tells us when I have coexistence between the liquid and vapor phases. So this is called the coexistence curve. All right, and so for this lower trace, what is that? That's probably around, let's see, 40, 50. So let's say that's around 48. So around 48, for this temperature, 13 degrees C, at 48 atmospheres, I expect to see two phases in equilibrium. This will correspond to the molar volume of the gas phase, and where this intersects with the x-axis will be the molar volume of the liquid phase, right? And then just keeping in mind that we know that the reciprocal of the molar volume gives us the density. So I could use these values to determine rho for the gas phase and rho for the liquid phase. Okay? All right, and one of the characteristics of the coexistence curve is as we increase the temperature and approach the critical point, we see that the difference between the molar volumes of the gas and liquid phases start to converge, and they become the same at the critical point. All right? And then the remaining curves, all right, so let me change this and do a little bit of highlighting. So for this curve and this curve and this curve, those all have temperatures that are greater than the critical point temperature, or greater than the critical temperature, right? So for these curves, T is greater than Tc, and these represent isotherms for supercritical fluids. All right, so the graph that we've shown corresponds to experimental data. And what we would want to do next is to show what our isotherms look like if we use our equations of state. So on this next slide, we've got our experimental data shown, and then we have isotherms that are calculated from the van der Waals equation and from the Redlich-Kwong equation, right? And we could also do it for the Peng-Robinson equation, right? And so we see, things that look quite similar. We look at the gas region, and we see that there's a pretty strong dependence of the molar volume on the pressure. And if we look at the liquid region, we see that the liquids are indeed not compressible. All right. We do see that there's this funny little shape here. All right. So we're not getting a clear coexistence curve. So we need to talk about that a little bit further. Right. What's the meaning of this? Well, this is an artifact of the fact that we have cubic equations. So a cubic polynomial gives rise to that functional shape. So what I'm going to do down below is I'm going to choose one of those isotherms and talk about how we utilize it. All right. So any one of those, I'm going to have pressure on this axis. I'm going to have molar volume on this axis. What we see is this sharp decline followed by a divot, a maxima, and then we fall off. All right. So that's one of our isotherms that we've calculated using either the van der Waals equation or the Redlich-Kwong equation. All right. And so we have to ask the question, how can I use this to determine where I have coexistence? And in order to do that, we use something called a Maxwell construction. So basically, a Maxwell construction means I draw a line in terms of the pressure such that area 1 and area 2 are equal to each other. Right? And when I do that, that gives me my molar volumes for my two phases. So this will be the molar volume of the gas phase, because again, this portion refers to gas behavior, and this corresponds to the molar volume of the liquid phase, because this portion corresponds to the liquid phase, right? And this would be an isotherm with a temperature under the critical point temperature. Okay? All right. And so by doing those Maxwell constructions, then we can generate our coexistence curve by passing through those. Right? I'm not much of an artist. Okay? All right. So again, in both of these curves, we have a critical temperature that gives us a critical point. Okay? All right, so we're going to talk about the cubic equation that corresponds to the coexistence region. So one of the things that we can see by looking at one of these isotherms, in the coexistence region, that would be F and G for these two graphs, right? We can see that there's 3 different roots to our polynomial, right? That smallest root is going to correspond to the molar volume of the liquid phase. And of course, if we know what that smallest root is, we can determine what the density, the molar density of the liquid phase, because that's going to be the reciprocal of the molar volume of the liquid phase. Right? And then our largest root, so let me just write F there because that's what it is on that figure. And the largest root is going to correspond to the gas phase. So it's the molar volume of the gas phase. And again, I can get the molar density of the gas or the vapor phase by taking the reciprocal. And that will correspond to the G portion of this. All right? So the intermediate root, that is at B, has no physical significance. All right, unfortunately, that just reminded me there was one other thing I was going to say about this previous graph. So what I want to do is talk about two regions here. All right, so I'm going to highlight this little region in blue. I'm going to highlight this little region in yellow. All right, and so if we have an equilibrium situation, we expect that at this pressure that we're going to have two phases, right? Now, if I do a rapid change, I might not reach equilibrium, all right? And so this curve that's above here is what we call metastable. And you can see that it lies on the gas side, so it's gas. Right? Whenever under the conditions when I'm sitting up there, I should be in the liquid phase. So this corresponds to supercooled gas. Right? So in that little region, if I exist there, that means that I'm not at equilibrium. I've made the change such that I'm sitting in the gas phase, but at that pressure, we should be in the liquid phase for equilibrium, so it's not going to be stable. In the yellow region, this is going to be also metastable. In this case, we're talking about liquid behavior. And in this pressure and temperature region, we expect actually to be in the vapor phase. So that means that what we've got here is superheated liquid. All right? And this is sort of a common thing that you observe if you have a microwave oven and put some water in it in a glass that has no scratches in it. Sometimes you heat it up, and when you add something to it, you find that all the water bubbles out. Well, that means that you've heated that beyond the vapor, beyond the boiling point, but there was nothing to nucleate the vaporization. So it suddenly goes towards equilibrium. So that's superheated liquid. Okay? All right. So the next thing that we want to do is talk about our EOS, our equation of state parameters. So this would be A, little a, big A, alpha, alpha, and lowercase b, capital B, and beta. Right? So that reflects the van der Waal equation, the Redlich-Kwong, and the Ping-Robinson. Right? So these values are determined from experiments. And specifically, they come from the critical temperature, the critical pressure, and the critical molar volume. All right? Which means on this graph, this point K is very, very important because that's where we can determine the parameters for A and B, alpha and beta. All right, there's two methods you can go about doing this, method 1 and method 2. Method 1 you guys are going to do on your own for homework 3. That's number 10. All right. And one of the things you may notice is that at this critical point, point K, the curve is changing from concave to convex. Right? That's known as a stationary inflection point. And you may recall from calculus that a stationary inflection point has some unique properties. The first is the first derivative of that function is equal to 0 at the stationary inflection point, and further, the second derivative of the function is equal to 0. Right? And so what you're going to be doing is looking at the pressure as a function of the molar volume for an equation of state. Right? And the first derivative of that will be dP dV. That's going to be equal to 0. So that's going to give you an equation. You also will recognize that the second derivative with respect to the molar volume is also equal to 0, and by taking the second derivative you have another equation. So this means that you have 2 equations, and that allows you to determine the relationship between the parameters A and B and the critical points. All right? So your goal will be to use this method to find that the critical molar volume is the same as 3 times B. The critical pressure is A over 27B squared. And the critical temperature is 8A over 27BR. Right? And so that's what you should find from solution of method 1 for the van der Waal equation. Right? There's another method, and that uses the cubic form of the equation of state, and we're going to talk about this specifically for the van der Waal equation. So our goal is to come up with these same results, right? Because it's the second method of getting the same end point, all right? And so what we can do is we can take our van der Waal equation that we've introduced previously, and we can write it in terms of a polynomial that's cubic with respect to the molar volume. All right. Now the thing that we're going to do is we're going to say, okay, this is the van der Waal equation written in the cubic form. All right. And we are going to specifically look at the critical point. So specifically at this critical point. So one of the things that we can say is at this inflection point, at the critical point, our 3 roots are identical, and further, the volume that we measure, that is what we expect to experimentally observe, is going to be the same as the molar volume at the critical point. Right? And what I can do is I can take this generic relationship and make that into a cubic polynomial. All right, so let's go ahead and do that. So this also means that V bar minus V bar at the critical point is equal to 0. So I've just done a quick rearrangement. And then I can cube both sides, and that tells me that the cube of the difference between the two is equal to 0. All right? Further, I can calculate out what this relationship is. So now, by expanding that, I get V bar cubed minus 3 V bar C V bar squared plus 3 V bar squared C V bar minus V bar cubed for the critical point. And that's all equal to 0. All right? So it's basically just doing some algebra. All right. Now, what I've derived here is totally general, right? It is general for any equation of state that is two parameter, right? So because all I've done is said at the critical point, my molar volume is the same as the critical molar volume, right? So what we're going to do now is we're going to compare. I'm going to call this equation 211. And I'm going to compare it with equation 210, right? And because they're describing the same thing, what we can say, let me highlight some things. All right, so here's v bar cubed, v bar cubed. Here's v bar squared, v bar squared, v bar, v bar. All right? And so what that tells us is that this term, b minus RT plus RT over P, is the same as 3 times the cubic, or 3 times the molar volume at the critical point. All right? And then my next term, let me change the color here real fast. I'll use purple. All right? So A over P will be the same as 3 times the molar volume at the critical point. Right? And then the last term is going to be identical between our two equations. So AB over P is the same as the cube of the molar volume at the critical point. All right? Okay, so we can use those identities to do some algebraic manipulation. So specifically looking at 210 and 211, I'm going to start by deriving 212a from the textbook. So we want an expression for 3 times the critical molar volume. All right? So 3 times the critical molar volume is here. And that tells me it is also here. All right, so we can say that 3 times the critical molar volume is the same as B plus RT over P. All right, because we are talking about being at the critical point, that means this is the critical temperature and the critical pressure. Right, so we have one identity that we're going to use in a little bit. All right, we can do the same thing. This is 212b from the textbook. So 3 times the critical molar volume squared, that's going to correspond to this term, right? And up above, that is going to be the same as A over P. So I can write in A over P. And again, because everything we're talking about is defined at the critical point, that's going to be A over the critical pressure, right? And then my last term, which corresponds to the critical molar volume cubed, that's going to be the same as AB over P. AB over PC. Okay? All right, so now what we want to do is simplify these things. Again, our goal is to come up with an expression for TC, for the molar volume, and for the pressure at the critical point. So that means we need to do a little bit of algebraic manipulation. Right? So let's focus on C first. So if I look at C, I realize I can rearrange this to make it A over the pressure. Right? And that's going to correspond to the critical molar volume divided by B. Right? And the thing that we notice is that this is identical to, so I'm going to put 2 asterisks there, that's identical to 212b. All right, and so what we can say at that point, because they are equal to each other, is that 3 VC squared is the same as VC cubed over B. All right, and we can do a simplification here. We recognize that we can get rid of, we can multiply, or we can divide both sides by V bar squared, right? And that's going to leave me with V bar, right? And that becomes V bar C equals 3 times B, right? And so that's the first expression that we've set out to determine. All right. So the next thing that we're going to do is we're going to try to come up with an expression for the pressure in terms of A and B. Right. So now we're going to go back to equation 212b. That's right there. All right. So let me just write that down. So 3vc squared. All right. Now we know at this point that the molar volume at the critical point is 3b. So I can square that, multiply that by 3. That becomes 27b squared. And that in turn is equal to A over PC. All right? And then what I can do is I can rearrange and say that PC is given by A over 27b squared. All right? And so we've determined our next critical parameter. All right? And then the last one that we're going to do is to determine an expression for the critical temperature. So here we go to equation 212a. All right? So I'm going to again write that down. So 3 times the critical molar volume. Well, we know that's going to be the same as 3 times 3b. Right? And that in turn is equal to 9b. All right, so that takes care of the left side. The right side will be B plus RTC over PC. All right, now I'm going to move this up a little bit. Okay. All right, so we have B in two places, so I can subtract B from both sides. That's going to give me 8B is equal to RTC over PC. Again, what we're looking for is an expression for the critical temperature. So I can say now the critical temperature will be given by 8B over R. Hang on, let me check my cheat sheet here. What did I do? We have 8B TC. Yeah. Oh, yeah. We're good. All right, and then I have PC in the numerator. All right. So what we've shown in the previous relationship, that PC is given by A over 27B squared, so we can substitute that in. So I have 8B over R times A over 27B squared. All right. And we see we can do a little bit of simplification there. The b's are going to cancel. So I end up with 8a over 27b times r. All right? And that's equal to our critical temperature. All right? So we have expressions for our three critical parameters. And that's what I've rewritten down below here. Okay? All right. And then what we want to just remind everybody of is that this means if I know A and B from tabulated data, I can calculate the critical pressure, molar volume, and temperature. But in general, we experimentally measure these values and then use those to determine A and B. So by doing the manipulation of two of these equations, we get expressions for A and B in terms of the critical parameters. So that's what we would use to determine A, and that's what we would use to determine B. All right. So just for the heck of it, what I want to do is talk about the critical point compressibility factor. All right. So this is going to be specifically for the van der Waal equation. All right. All right. And we keep in mind that when we're calculating this critical or this compressibility factor, we're talking about being at the critical point. So this isn't really going to be ideal gas behavior. This is going to be, pretty close to supercritical fluid. It's on the border of supercritical fluid and liquid and the vapor phases. At any rate, that means that I want to calculate P V bar C over R T C. Okay? All right. And what I'm going to do is one by one substitute in my relationships in terms of parameters A and B. So PC is going to be A over 27B squared. All right, so there I've put in the pressure. Next up, I'm going to put in the molar volume. That's going to be times 3B. All right, and then I'm going to divide it by R. All right, so I'm going to put in 1 over R. And then my final one is to put the reciprocal of the critical temperature. So because we're dividing by the temperature, that basically means I can take the reciprocal of this expression. So that's going to give me 27BR divided by 8A. All right? And I know that looks like a mess right now, but we recognize we're going to be able to do some simplification. All right? So one of the things that we see is that we have an A in the numerator and A in the denominator. So that's going to cancel. All right? Let me go to another color real fast. All right, let's go to violet. All right? And then I look at B's, and I see that I've got a B in the numerator and another B in the numerator, so that's B squared. That cancels with that B. All right? And then the other thing that we recognize is that we've got an R in the denominator and an R in the numerator. All right? And we have a 27 in the numerator and a 27 in the denominator. And we end up with 3/8. Okay? All right, so this is basically saying that no matter what gas I have, if I'm at the critical point, we expect to see the compressibility factor as a constant, right? And that is sort of weird and it's intriguing, all right? So this also says at the critical point, gases all behave, or these fluids all behave the same. So same value, no parameters, all substances. All right, we're going to come back to this on pages 16 and 17 whenever we get there in the lecture notes. All right, so let's just take a look at what happens if we do the same sort of analysis for the Redlich-Kwong and for the Peng-Robinson equations of state. All right, so using the methodology that we've outlined previously, we can determine the relationship between our parameters A and B and the critical molar volume, the critical pressure, the critical temperature. And we would follow the same techniques that we've just introduced. And by using the critical temperature and pressure, we can say how we determine empirically parameters A and B. All right? So the other thing that we notice is that if we look at the compressibility factor at the critical point using the Redlich-Kwong, we find that it's 0.333, or 1/3. Right? And that's interesting. It predicts the same result as the van der Waal equation. I have a parameter-free compressibility factor at the critical point. Right? For the Peng-Robinson, we're just going to look at the critical point. Right? And for the critical point, we find that it's going to be 0.3074. So all of our equations of state all predict Z critical is a constant for all substances. Okay? Well, let's see what experimental data looks like. So this is critical constants for a whole mess of different substances. So I just want to look at the temperature first. Well, one of the things we see is that we have wide variability. So we have small critical temperatures, large critical temperatures, super large critical temperatures. So they vary all over the place. I have two columns of pressure, one for each pressure unit, bar or atmosphere. And we see the same thing. We see large values of the critical pressure, and we see small values of the critical pressure. Similarly for the molar volume. So this would be decimeters cubed per mole or liters per mole. All right? So wide variability. Our last column, we're calculating the compressibility factor for the critical point. And again, this is experimental. And one of the things that we see is that indeed we do see things converging to a constant, all right? So if I calculate the average of this group, I find that it's 0.28. So all of them are sort of close to that ballpark, right? So that tells us that there's something innate about the critical point, right? Just a side note. So we see that 0.28, that's going to be closest to the constant that's associated with the Peng-Robinson equation of state. And if we think about it, we've said that at the critical point, we've got the supercritical fluid, so we have liquid, we have vapor, and supercritical fluid, all right? Which means we're near the liquid-vapor equilibrium, which is where the Peng-Robinson equation of state works better, all right? So that's all self-consistent. All right, this leads us to the law of corresponding states. Right? And we'll be demonstrating this in a variety of different ways. So what we can say, the law of corresponding states, is that the properties of all fluids are the same as long as we're comparing the fluids at the same conditions relative to the critical point. Right. Up to this point, we've only demonstrated that all fluids behave the same at the critical point. We're extending that to say they all behave the same as long as we're looking relative to the same critical point. And I just want to make sure that we add to this that by fluid, we're referring to liquids, gases or vapor phase, and supercritical fluids. All right, then the question is, what do we mean by relative to the critical point? All right, and unfortunately, that was my timer, and that says this is a point where I have to stop, so this will be a cliffhanger. We'll pick up there on Friday, assuming it's warm enough to go to class on Friday. But what we're going to talk about next time is what do we mean by relative to the critical point? And a little bit further foreshadowing. Right? So the law of corresponding states, what that tells us is that if we're able to define our variables relative to the critical point, we expect to be able to write equations of state that have no parameters. And if you think about it, that's pretty powerful. That's where we'll leave it for today. Stay warm, get started on your homework, and good luck with all.